So now I'm going to start making use of those analysis techniques that we've gone over so far. And in order there's a certain set of devices that we're going to analyze specifically. Okay, um, and I'm going to just go briefly over what they are. And this here will be posted on the Canvas and everything, so you can refer to it whenever you'd like. But they come in a couple different classes. All right, we got nozzles and diffusers. That's really just a geometric. Um, it's just a geometry of a duct, say. So you can have certain geometries where we're compressing the flow down into a smaller cross-sectional area, and as a consequence, the velocity increases. Okay, that's called a nozzle. If we do the opposite, the velocity, the main purpose of a diffuser, which would be the opposite configuration. Basically, if I run the nozzle backwards, I get a diffuser, and the purpose of the diffuser is to close or slow the flow down. So the velocity of the fluid entering the diffuser is much greater than when it exits. And there's a few assumptions that you can make when when analyzing nozzles and diffusers. Mainly, they're typically taken to be adiabatic, so Q is 0. There's no work interaction. That's obvious just from looking at it. There's no work interaction, and I mean, unless they're gigantic or something like that, you can take the elevation to be the same. So there's not going to be any change in potential energy as the fluid passes through the nozzle. Then you have turbines and compressors, which are really a way of extracting or inputting work into a fluid. So if you have uh, fluid entering at a much lower pressure and coming out, a compressor does exactly what it says it does. It pressurizes the fluid. Okay, so inputs work and takes a fluid at a low pressure and produces a fluid at a high pressure. A turbine does the opposite. It takes fluid at a high pressure, uh, expels it at a low pressure, and in the process extracts a certain amount of work. Uh, and the typical assumptions, typically, again, we assume that these are adiabatic. Um, Not always, but if you're given information regarding the heat, then you can take this to be not true. But if you're not given any information regarding the heat escaping or entering the turbine or compressor, you can take it to be adiabatic. I shouldn't leave you hanging like that. I'll probably it'll be a mistake if I don't tell you exactly that the nozzle is adiabatic. I usually throw that keyword in there anyway. So the velocity, the change in velocity, another assumption that the change in velocity as the fluid enters or leaves the device is negligible when compared to, say, the work input. Or so basically, the change in kinetic energy of the fluid as it enters or leaves the device is negligible when compared to the sort of the thermal energy change of the fluid. Okay, and in comparison to the workout, so the the change in kinetic energy is usually taken to be negligible unless otherwise told. All right, and then again, unless these devices are gigantic, the change in potential energy is also 0. Now, these class of um, devices also cover things like pumps and fans and things like that. They're similar. Yeah, you know what I mean. So the next thing that we have is what we call a throttling valve, and it's usually just a very easy, simple device. It's just a restriction in the flow. So we go from uh, high pressure on one side, it gets restricted, and what escapes on the other side is low pressure. And, it could be a valve. It could be like basically a porous plug in the fluid. And then oftentimes what you'll see in like air conditioners and stuff, you'll see just a really thin tube, So you have just a really thin tube, and the drag that the fluid feels as it is pushed through that thin tube acts as a throttling valve. So they just produce huge, large pressure drops from one side of the plug to the other. Now the assumptions here are that the pressure on the downstream side is going to be much less than the pressure on the upstream side. The change in kinetic energy is essentially zero. The change in potential energy is essentially zero. There's no work or heat interaction. They're typically considered to be adiabatic. Uh, for our purposes, they'll be considered to be adiabatic. Now, it doesn't leave a whole lot. So really what you wind up doing here is you're exchanging flow work for internal energy. That's what you're doing. And we'll get into details here in the examples. And then you just have the evaporators and condensers. And essentially, these can be thought of as the exact sort of, the complementary device to the turbines and compressors, except where we're extracting work, inputting or extracting work in the turbines and compressors. Here, we're just inputting and extracting heat. And usually, these things are just devices with a lot of fins on them and stuff like that that basically accentuate the rate at which heat can leave one device from the other. And then the assumptions are essentially the same as turbines and compressors, except instead of being adiabatic, there's no work input, there's no work interaction. And so that's basically a summary of the devices that we're going to be covering.